Quantum dawn, a new era of computing. Welcome, curious minds, to a journey into the most profound frontiers of technology, the realm of quantum computing. For decades, our digital world has been powered by classical computers, brilliant machines that process information in bits, representing either a 0 or a 1. From the smartphones in our pockets to the supercomputers mapping weather patterns, these devices have reshaped our lives. But imagine a different kind of computer, one that doesn't just process information sequentially, but simultaneously, exploring a mind-boggling array of possibilities all at once. This is the promise of quantum computing, a paradigm shift that could unlock solutions to problems currently deemed impossible. At the heart of this revolution stands a name that has reverberated through the scientific community: Sycamore. Google's quantum processor, Sycamore, isn't just another step in technological advancement. It's a monumental leap into an entirely new dimension of computational power. It's a testament to human ingenuity and our relentless pursuit of understanding the fundamental nature of reality itself. To truly grasp the significance of Sycamore, we must first understand the limitations of classical computing and why a quantum approach is not just an alternative, but a necessity for tackling the grand challenges of the 21st century. Classical computers, no matter how fast, are inherently bound by their binary nature. They process information in a linear fashion, crunching numbers one operation at a time. While incredibly efficient for many tasks, this approach hits a wall when faced with problems that involve an astronomical number of variables and interdependencies. Think about simulating complex molecular structures for drug discovery, optimizing global logistics networks, or even cracking some of the most advanced encryption methods. These are problems where the number of possible solutions explodes exponentially, far exceeding the capacity of even the most powerful classical supercomputers to explore within any reasonable time frame. Quantum computing, on the other hand, operates on entirely different principles, drawing from the bizarre and counterintuitive laws of quantum mechanics. It's a field that forces us to re-evaluate our everyday understanding of reality, where particles can exist in multiple states simultaneously and influence each other instantaneously across vast distances. This foundational difference is what gives quantum computers their extraordinary potential. Sycamore is a physical manifestation of these abstract quantum principles, a meticulously engineered device designed to harness these strange phenomena for computational advantage. It's a machine built to transcend the binary limitations, to explore a universe of possibilities in ways that classical computers can only dream of. The implications of such a device are staggering, touching upon everything from medicine and materials science to artificial intelligence and our fundamental understanding of the universe. In the coming chapters, we will delve deeper into the marvels of Sycamore, exploring its architecture, its unparalleled power, and its potential to illuminate the darkest corners of quantum mechanics. Prepare to have your mind expanded as we journey into the quantum dawn. The building blocks of quantum power, qubits and superposition. At the heart of Sycamore, and indeed all quantum computers, lies the qubit, the quantum equivalent of the classical bit. But a qubit is far more extraordinary than its binary counterpart. Unlike a classical bit, which can only be in a state of 0 or 1, a qubit can exist in both states simultaneously, thanks to a peculiar quantum phenomenon called superposition. Imagine a spinning coin that, while in the air, is neither heads nor tails, but a probabilistic combination of both. Only when it lands and is observed does it collapse into a definite state. Qubits behave similarly. This ability to be in multiple states at once is not just a curiosity, it's a fundamental source of quantum computing's power. A single qubit in superposition can effectively store and process information about both 0 and 1 simultaneously. 2 qubits in superposition can represent 4 states at once: 0, 0, 0, 1, 1, 0, 1, 1, and so on. As the number of qubits increases, the number of states they can simultaneously represent grows exponentially. This exponential scaling is what gives quantum computers their mind-boggling potential. A quantum computer with just a few dozen stable qubits can explore more possibilities simultaneously than the most powerful classical supercomputers could ever hope to process sequentially. Sycamore, specifically, utilized 53 superconducting qubits, meticulously arranged in a two-dimensional grid. These qubits are tiny circuits, chilled to temperatures colder than deep space, just a few thousandths of a degree above absolute zero. This extreme cold is crucial to minimize environmental interference, which can cause the delicate quantum states of the qubits to decohere, losing their quantum properties and collapsing into classical states. Maintaining these fragile quantum states is one of the greatest engineering challenges in quantum computing. The qubits in Sycamore are made from superconducting materials, allowing electrons to flow without resistance, creating a macroscopic quantum effect. When cooled sufficiently, these circuits exhibit quantum mechanical properties, allowing them to enter superposition. These aren't just theoretical constructs. They are real, physical systems meticulously engineered to harness the bizarre rules of the quantum world. The superconducting circuits act as artificial atoms, and their energy levels can be manipulated to represent the 0 and 1 states. By carefully applying microwave pulses, researchers can nudge these qubits into superposition, creating the probabilistic blend of states that is so vital to quantum computation. The design of these qubits and their intricate connectivity within the Sycamore chip are the culmination of decades of research in quantum physics and engineering. Each qubit is a marvel of miniaturization and precision, a testament to the cutting edge of materials science and cryogenic technology. Understanding superposition is the first step in appreciating the true power of Sycamore. It's not just about faster processing, it's about a fundamentally different way of processing information, one that mirrors the inherent probabilistic nature of reality itself. In the next chapter, we'll explore another equally strange and powerful quantum phenomenon that Sycamore leverages: entanglement. The fabric of quantum reality, entanglement, and quantum parallelism. If superposition is the ability of a qubit to be in multiple states at once, then entanglement is the ability of multiple qubits to become inextricably linked, their fates intertwined no matter the distance separating them. Imagine two coins that, once entangled, always land on the same side, even if you flip them in different cities. The outcome of one instantly influences the other, not through any physical connection, but through a deeper, more mysterious quantum correlation. This spooky action at a distance, as Einstein famously called it, is not only real, but is another cornerstone of quantum computing's power. When qubits are entangled, their individual states are no longer independent. They are part of a larger, collective quantum state. Measuring one entangled qubit instantaneously reveals information about its entangled partners, regardless of how far apart they are. This non-local correlation allows quantum computers to perform operations on multiple qubits simultaneously, leading to what's known as quantum parallelism. This is where the magic truly happens. Instead of performing calculations one by one, a quantum computer can, through superposition and entanglement, explore a vast number of computational paths simultaneously. It's like having an army of parallel universes, each trying a different solution to a problem, and then magically converging on the correct answer. Sycamore's architecture was specifically designed to facilitate robust entanglement between its 53 qubits. Each qubit is connected to 4 nearest neighbors, forming a lattice that allows for complex interactions and the creation of highly entangled states. These connections are crucial for performing quantum gates, which are the quantum equivalents of logical operations in classical computers. However, unlike classical gates that operate on definite zeros and ones, Quantum gates manipulate the probabilities and phases of superpositioned and entangled qubits. The ability to create and maintain strong entanglement among a large number of qubits is one of the most challenging aspects of building a quantum computer. Environmental noise, even tiny vibrations or stray electromagnetic fields, can easily break these delicate quantum links, causing the qubits to decohere and lose their entanglement. Google's engineers spent years perfecting the control mechanisms and shielding techniques necessary to achieve the level of entanglement observed in Sycamore. This involved designing extremely stable and precise microwave control pulses to manipulate the qubits without disturbing their quantum states. The development of Sycamore was not just about building a chip, it was about mastering the art of controlling the fundamental fabric of reality at an unprecedented scale. The interplay between superposition and entanglement allows Sycamore to tackle problems that are beyond the reach of classical computers. It's not just about speed, it's about a fundamentally different way of computing, one that harnesses the inherent parallelism and interconnectedness of the quantum world. The implications for fields like drug discovery, materials science, and artificial intelligence are profound. By understanding entanglement, we begin to grasp how Sycamore can explore vast computational landscapes in a way that classical computers simply cannot. In the next chapter, we will delve into the groundbreaking experiment that catapulted Sycamore into the global spotlight, the demonstration of quantum supremacy. The quantum supremacy milestone, Sycamore's triumph. In October 2019, Google announced a monumental achievement that sent ripples through the scientific and technological communities worldwide. They had demonstrated quantum supremacy with their Sycamore processor. This wasn't just another incremental step, it was a watershed moment, a proof of concept showing that a quantum computer could perform a specific computational task demonstrably faster than the most powerful classical supercomputers available. The task chosen for this demonstration was intentionally artificial, designed to be extremely difficult for classical computers, but relatively straightforward for a quantum machine leveraging superposition and entanglement. It involved sampling the output of a random quantum circuit. Imagine throwing a complex set of quantum dice and predicting the exact distribution of their outcomes. For a classical computer, calculating these probabilities for a sufficiently large number of qubits requires an astronomical amount of time and memory. Google's team estimated that the fastest supercomputer in the world at the time, IBM's Summit, would have taken approximately 10,000 years to complete the task that Sycamore finished in a mere 200 seconds. While there was some debate about the exact classical compute time required, the overwhelming consensus was that Sycamore had achieved a significant and undeniable computational advantage. This wasn't about solving a practical problem that had immediate real-world applications. It was about proving the fundamental capability of quantum computers to outperform classical ones on a specific, challenging task. It was like the Wright brothers' first flight, not immediately useful for commercial travel, but a clear demonstration that powered flight was possible. The quantum supremacy experiment was a testament to the meticulous engineering and theoretical understanding that went into building Sycamore. It validated decades of research and billions of dollars of investment in quantum computing. The experiment involved carefully preparing the 53 qubits in a specific initial state, applying a sequence of precisely timed microwave pulses to create a complex entangled state, and then measuring the final states of the qubits. The results were then compared to theoretical predictions, confirming that Sycamore was indeed performing the intended quantum computation. The significance of quantum supremacy cannot be overstated. It shifted quantum computing from a theoretical possibility to a demonstrable reality. It ignited a global race among tech giants and nations to develop ever more powerful and stable quantum computers. It also provided crucial validation for the underlying principles of quantum mechanics when applied to complex computational systems. While Sycamore's initial task was abstract, the implications for future practical applications are immense. Once quantum computers can reliably perform tasks beyond classical capabilities, the doors open to revolutionary breakthroughs in various fields. The achievement was not without its critics, primarily from competitors who argued that classical computers could perform the task faster than Google claimed. However, even with these adjustments, the core message remained. Quantum computers had demonstrated a fundamentally different and more powerful computational paradigm. This milestone marked the beginning of a new chapter in the history of computing, one where the boundaries of what's computationally possible are being dramatically redefined. The era of quantum advantage, where quantum computers routinely outperform classical ones on practically useful tasks, is now firmly on the horizon, thanks in no small part to Sycamore's pioneering achievement. The architecture of a quantum marvel, Sycamore's design. To truly appreciate Sycamore's triumph, we must delve into its intricate architecture and the engineering marvels that lie beneath its superconducting surface. Sycamore is not a desktop computer. It's a highly specialized piece of equipment housed in a custom-built dilution refrigerator, an elaborate cryogenic system designed to cool the chip to extremely low temperatures, just 15 millikelvin, colder than interstellar space. This extreme cold is absolutely critical because quantum states are incredibly fragile. Any thermal energy or environmental noise can disrupt the delicate superposition and entanglement, causing the qubits to decohere and behave classically. The dilution refrigerator acts as a sanctuary, isolating the Sycamore chip from the warm, noisy world outside. The chip itself is a thin wafer of silicon, onto which superconducting circuits are patterned using advanced nanofabrication techniques. These circuits form the 53 qubits, each a tiny tunable resonator. Specifically, Sycamore uses transmon qubits, a type of superconducting qubit known for its relatively long coherence times and strong coupling to microwave control signals. Each transmon qubit consists of a capacitor and a Josephson junction, a quantum mechanical tunnel junction that allows superconducting currents to flow through a thin insulating barrier. This non-linear element is crucial for creating the anharmonicity required to manipulate the qubit's energy levels precisely. The qubits are arranged in a two-dimensional grid, with each qubit directly connected to 4 of its nearest neighbors. This heavy hex lattice connectivity is a key feature of Sycamore's design, allowing for efficient entanglement generation and complex quantum operations across the chip. The ability to couple qubits strongly and controllably is essential for building complex quantum circuits. Microwave control lines are meticulously routed to each qubit, allowing researchers to precisely tune their energy levels and apply specific microwave pulses. These pulses act as quantum gates, manipulating the quantum states of individual qubits, single qubit gates, or creating entanglement between pairs of qubits, 2-qubit gates. The timing and amplitude of these pulses must be incredibly precise, often on the order of nanoseconds, to avoid introducing errors into the fragile quantum computation. The control electronics that generate and deliver these microwave pulses are themselves a marvel of engineering, located outside the cryogenic environment and connected to the chip via numerous coaxial cables that are designed to minimize heat conduction. Error correction is another critical aspect of quantum computer design, though Sycamore was a noisy intermediate-scale quantum (NISQ) device, meaning it did not incorporate full quantum error correction. Future quantum computers will require sophisticated error correction schemes to build fault-tolerant quantum computers that can perform computations without being overwhelmed by noise. However, Sycamore's design prioritized maximizing the number of qubits and their connectivity while maintaining sufficient coherence times to demonstrate quantum supremacy. The entire setup, from the cryogenics to the chip fabrication and the control electronics, represents a triumph of interdisciplinary engineering, combining quantum physics, materials science, electrical engineering, and computer science. Sycamore's design is a testament to the immense complexity and meticulous precision required to build and operate a functioning quantum computer. It's a glimpse into the future of computing hardware, where the rules of the quantum world are not just observed, but actively engineered and harnessed for unprecedented computational power. Beyond supremacy, what's next for quantum computing? While Sycamore's demonstration of quantum supremacy was a monumental achievement, it was just the first step on a long and challenging journey towards practical, fault-tolerant quantum computing. The immediate impact of quantum supremacy wasn't about solving real-world problems directly, but about proving the fundamental potential of this new computational paradigm. So, what comes next? The roadmap for quantum computing is multifaceted, involving advancements in several key areas. Firstly, increasing the number of qubits is paramount. Sycamore's 53 qubits were sufficient for the supremacy experiment, but many practical quantum algorithms will require hundreds, thousands, or even millions of stable, interconnected qubits. This is a significant engineering challenge, as adding more qubits generally increases complexity and the potential for errors. Researchers are exploring various architectures and materials to scale up quantum processors, including different types of superconducting qubits, trapped ions, photonic qubits, and topological qubits, each with its own advantages and disadvantages. Secondly, improving qubit quality and coherence times is crucial. Even with Sycamore, the qubits were noisy, meaning their quantum states were susceptible to errors and decoherence. For quantum computers to reliably solve complex problems, they need much longer coherence times and lower error rates. This involves better materials, improved shielding from environmental noise, and more precise control over the qubits. Research is actively focused on understanding and mitigating various sources of error, from thermal fluctuations to electromagnetic interference and imperfections in fabrication. Thirdly, developing robust quantum error correction, QEC, is essential. Unlike classical error correction, which simply copies information, quantum error correction is much more complex due to the no-cloning theorem. You can't perfectly copy an unknown quantum state. QEC involves encoding quantum information redundantly across multiple physical qubits to protect it from errors. However, implementing QEC schemes requires a significant overhead of physical qubits for each logical, error-corrected qubit, making it a major challenge for scalability. Fourthly, developing practical quantum algorithms is as important as building the hardware. While algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases have shown exponential speed-ups, many more algorithms are needed to tackle a wider range of problems. Researchers are actively developing new quantum algorithms for materials science, drug discovery, financial modeling, artificial intelligence, and more. This often involves a deep understanding of both quantum mechanics and the specific problem domain. Finally, bridging the gap between quantum hardware and classical control systems is an ongoing area of innovation. Quantum computers are not standalone devices. They require sophisticated classical computers to control them, interpret their results, and integrate them into larger computational workflows. This involves developing new quantum programming languages, compilers, and operating systems that can effectively manage the unique challenges of quantum computation. The journey from Sycamore's supremacy to truly fault-tolerant, universal quantum computers capable of solving a wide array of practically relevant problems will be long and arduous, likely spanning decades. However, the progress made with Sycamore has demonstrated that this future is not just a dream, but a tangible goal that is being actively pursued by scientists and engineers worldwide. The next generation of quantum processors will build upon Sycamore's legacy, pushing the boundaries of what's computationally possible and bringing us closer to a quantum-powered future. How quantum computers help us understand quantum mechanics. One of the most profound, yet often overlooked benefits of building quantum computers, like Sycamore, is their potential to deepen our understanding of quantum mechanics itself. For decades, quantum mechanics has been a notoriously counterintuitive and abstract theory, described by complex mathematical equations that often defy our classical intuition. Richard Feynman famously suggested that nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. This is precisely where quantum computers shine. Simulating quantum systems on classical computers is incredibly difficult, often impossible, because the computational resources required grow exponentially with the size and complexity of the quantum system being simulated. A classical computer trying to model the interactions of just a few dozen entangled particles quickly becomes overwhelmed by the sheer number of possible quantum states. This limitation has historically hampered our ability to truly see and understand the intricate workings of quantum phenomena. Quantum computers, by their very nature, are quantum mechanical systems. They operate under the same rules as the particles they are trying to simulate. This means they can intrinsically mimic the behavior of other quantum systems. Instead of trying to calculate every possible quantum state, a quantum computer can directly emulate the evolution of a quantum system, essentially running a miniature quantum experiment within its own architecture. For example, quantum computers can be used to simulate the behavior of molecules, predicting their chemical reactions, energy levels, and material properties with unprecedented accuracy. This capability is invaluable for materials science, allowing researchers to design new superconductors, catalysts, or drug molecules from first principles, without relying solely on trial and error. By running quantum simulations on Sycamore or its successors, scientists can gain insights into complex quantum phenomena that are currently intractable. They can explore exotic states of matter, investigate the properties of high-temperature superconductors, or even shed light on the fundamental nature of black holes and the early universe. The ability to program a quantum computer to mimic another quantum system allows physicists to test theoretical models and hypotheses in ways that were previously impossible. They can essentially run experiments on a quantum computer that would be too difficult, too expensive, or even physically impossible to conduct in a laboratory setting. This feedback loop between theoretical physics and experimental quantum computing is crucial for advancing our understanding of the universe at its most fundamental level. Furthermore, the very act of building and controlling quantum computers forces physicists and engineers to confront the practical challenges of harnessing quantum mechanics. The painstaking effort to maintain qubit coherence, minimize errors, and design efficient quantum gates provides invaluable empirical data that can refine our theoretical models. Understanding why qubits decohere or how entanglement can be robustly maintained directly contributes to our fundamental knowledge of quantum interactions. In essence, quantum computers are not just tools for solving problems, they are laboratories for exploring the very fabric of reality. They allow us to probe the strange and wonderful world of quantum mechanics with unprecedented detail, potentially unlocking new discoveries about the universe and ourselves. Sycamore has paved the way for this exciting new era of quantum exploration, where the boundaries between computation and discovery blur into a single profound quest for knowledge. Quantum's real-world impact, beyond the lab. While the Sycamore experiment focused on an abstract problem, the ultimate goal of quantum computing is to solve real-world problems that have a tangible impact on humanity. The potential applications span across virtually every scientific and industrial sector, promising to revolutionize how we approach some of our biggest challenges. One of the most promising areas is materials science and chemistry. Imagine designing new materials with specific properties from scratch, rather than through trial and error. Quantum computers can simulate molecular interactions with far greater accuracy than classical machines, leading to the development of novel drugs, more efficient catalysts, high-temperature superconductors, or advanced battery technologies. For example, understanding the complex electron interactions within a molecule is crucial for drug discovery. Quantum computers could accurately model these interactions, accelerating the development of new medicines for diseases like cancer, Alzheimer's, or even pandemic viruses, significantly reducing the time and cost associated with drug development. Another transformative application lies in optimization problems. Many real-world challenges involve finding the best solution from an astronomically large number of possibilities. This includes optimizing global supply chains, scheduling complex logistics, designing more efficient transportation networks, or even managing financial portfolios. Quantum optimization algorithms could find optimal solutions far faster than classical methods, leading to massive efficiencies and cost savings across industries. For example, optimizing airline schedules to minimize delays and fuel consumption, or designing smart grids that efficiently distribute renewable energy. Artificial intelligence and machine learning stand to gain significantly from quantum computing. Quantum machine learning algorithms could process vast data sets and recognize patterns in ways that classical AI cannot, leading to more powerful and intelligent AI systems. This could translate into more accurate medical diagnoses, better fraud detection, or even the development of truly sentient AI. Imagine a quantum-powered AI that can learn from sparse data, overcome biases, and make highly nuanced decisions. In finance, quantum computers could be used for more accurate financial modeling, risk analysis, and algorithmic trading. Complex financial derivatives and market simulations currently strain classical computing resources. Quantum algorithms could perform these calculations with greater speed and precision, offering unprecedented insights into market behavior and investment strategies. Lastly, cryptography is an area where quantum computing presents both a threat and an opportunity. Shor's algorithm, if run on a sufficiently powerful quantum computer, could break many of the encryption methods currently used to secure our digital communications, banking, and sensitive data. This has spurred a global race to develop post-quantum cryptography, new encryption schemes designed to be resistant to quantum attacks. Simultaneously, quantum mechanics also offers new avenues for secure communication through quantum key distribution, providing theoretically unbreakable encryption. While these applications are still some years away from widespread commercial deployment, the progress made with Sycamore has demonstrated the fundamental viability of building machines capable of these feats. The journey from scientific curiosity to real-world impact is accelerating, and the future promises a world where quantum computing fundamentally reshapes our technological landscape, solving problems we once thought insurmountable. The challenges ahead, building the quantum future. While Sycamore marked a pivotal moment, the path to universal fault-tolerant quantum computing is fraught with significant challenges. Building a quantum computer is not simply about scaling up. It involves overcoming fundamental scientific and engineering hurdles that push the boundaries of current technological capabilities. The primary challenges can be broadly categorized: qubit stability and coherence. As we discussed, qubits are incredibly fragile. Maintaining their quantum states, superposition and entanglement for long enough to perform complex calculations is extremely difficult. Environmental noise, stray electromagnetic fields, vibrations, even minute temperature fluctuations can cause qubits to decohere, losing their quantum properties and introducing errors. Researchers are constantly working on better isolation techniques, more robust qubit designs, and more sophisticated control methods to extend coherence times. Error rates and error correction. Current quantum computers, including Sycamore, are noisy by classical standards. Every operation on a qubit has a certain probability of error. For complex algorithms, these errors accumulate rapidly, rendering computations unreliable. Quantum error correction, QEC, is the theoretical solution, but implementing it is incredibly resource-intensive. A single logical, error-corrected qubit might require hundreds or even thousands of physical qubits to protect its information. Building quantum computers with enough physical qubits to support practical QEC is a monumental engineering challenge. Scalability. Sycamore had 53 qubits. While impressive, many practical quantum algorithms will require thousands or even millions of stable, high-quality qubits. Scaling up quantum processors without introducing excessive noise or fabrication defects is a major hurdle. This involves developing new manufacturing techniques, innovative chip architectures, and efficient ways to connect and control a vast number of qubits. Control and connectivity. Precisely manipulating individual qubits and creating entanglement between them requires extremely sophisticated control electronics and precise microwave pulsing systems. As the number of qubits increases, the complexity of these control systems grows exponentially. Efficiently routing control signals to each qubit within a cryogenic environment, minimizing crosstalk and interference, is a non-trivial task. Software and algorithms. The hardware is only half the battle. We also need to develop powerful quantum software, programming languages, compilers, and operating systems that can harness the unique capabilities of quantum hardware. Furthermore, discovering and optimizing new quantum algorithms for a wide range of problems is an ongoing area of research. Not all classical problems will benefit from quantum speedup, and identifying those that do is crucial. Cryogenics and infrastructure. The extreme cold required for superconducting qubits necessitates complex and expensive dilution refrigerators. Scaling these cryogenic systems to accommodate larger quantum processors while maintaining the required ultra-low temperatures and vibration isolation presents significant engineering challenges. The infrastructure surrounding quantum computers is itself a highly specialized field. Despite these formidable challenges, the global scientific community is making remarkable progress. Breakthroughs in materials science, nanofabrication, and quantum control are steadily pushing the boundaries. The lessons learned from pioneering machines like Sycamore are invaluable, providing critical insights into the real-world complexities of building a quantum future. The journey will be long and arduous, but the potential rewards are so immense that the pursuit continues with unwavering determination. The next generation of quantum computers will build upon these foundational insights, slowly but surely overcoming these obstacles on the path to a quantum-powered future. The quantum future, a glimpse into tomorrow. As we conclude our journey through the quantum realm of Sycamore, we look towards a future where quantum computing moves beyond the laboratory and into widespread application. The vision of the quantum future is not about replacing all classical computers. Rather, it's about complementing them, providing a specialized, immensely powerful tool for problems that are simply intractable for classical machines. Imagine a world where drug discovery is radically accelerated, leading to cures for currently incurable diseases within years, not decades. New materials with previously unimaginable properties, perhaps room-temperature superconductors or highly efficient solar cells, could revolutionize energy, transportation, and manufacturing. Financial markets could be more stable and efficient, with risks precisely modeled and mitigated. Artificial intelligence could achieve unprecedented levels of understanding and problem-solving, leading to breakthroughs in scientific discovery, personalized medicine, and human-computer interaction. Secure global communication networks, protected by the unhackable laws of quantum mechanics, could safeguard our most sensitive data. Climate change models could become vastly more accurate, allowing us to predict and mitigate environmental disasters with greater precision. While the full realization of this quantum future may still be decades away, the groundwork laid by pioneers like Sycamore is accelerating its arrival. Research is advancing rapidly on multiple fronts, from hardware development across various qubit modalities to the creation of new quantum algorithms and software tools. Global collaborations between academic institutions, tech giants, and government agencies are pooling resources and expertise to overcome the remaining challenges. The investment in quantum computing is immense, reflecting the universal belief in its transformative potential. However, the quantum future also brings with it ethical considerations. The ability to break current encryption schemes necessitates a proactive approach to developing quantum-resistant cryptography. The power of quantum AI raises questions about responsible development and societal impact. These are conversations that must happen now, alongside the technological advancements, to ensure that the quantum revolution benefits all of humanity. Sycamore has shown us that the quantum realm is not just a theoretical construct. It is a tangible, programmable reality. It has opened a door to a new era of computation, one that promises to unlock solutions to some of humanity's most pressing problems and deepen our understanding of the universe itself. The journey ahead is exciting, challenging, and filled with the promise of unprecedented discovery. The quantum future is not a distant dream. It's being built, qubit by qubit, right now, changing the very fabric of our technological world. Thank you for joining us on this exploration of Google's Sycamore and the incredible potential of quantum computing. The future is quantum, and it's already here.